We're glad to attend this conference with the invitation of Professor Tang. Thank you so much, Professor Tang, for inviting me. My name is Yong Xie. I'm from Xiden University and ICMM. Unfortunately, I cannot attend this conference in person at this moment because of some the war of Iran, and so. But still, I want to share my idea about how to combine artificial intelligence with 2D material and devices. So my talk will categorize in these different parts. First, I will tell a little bit about the motivation, and then in three different examples, I will show how can I apply artificial intelligence to 2D material and device research. So as we are this famous conference for integrated circuit, I hope everybody, I assume everybody know that Moore's law and also the importance of Moore's law, and also especially for industry people, that you are more focusing on mineralization of the Moore's law. But as a researcher in academia with limited resources, basically what we can do is we want to bring more new ideas, bring more multifunctionality and diversity to this community. Therefore, my research is focused more on the more than more domain. So for the application of 2D materials, especially for the Chinese, we are very strong this research topic, and we also built a very famous integrated circuit already with the 2D materials. So like MS2. So for my research, I made more on the photo detector side, and also I use strain as the tuner knob to tune the property of the band gap of the 2D material. Then the electrical and optical and optoelectronics property of the 2D material will change in respect to strain. So in order to have better performance of a device, we need to have better control of synthesis of 2D materials. In order to speed up the research of the synthetics of 2D materials, we need highly demanded this kind of closed loop synthesis of the material. What does that mean? My vision is like for either MS2 or other 2D materials with MOCVD or CVD growth, what we are lacking of is the reproducibility. Why? Because every user have its own habit. How can we avoid that? We need the incorporation of the artificial intelligence and robotics. So we have the different parameters of the growth, but for the characterization, we need to a massive and also a high throughput characterization. So then we need a feedback loop using the robotic arms. But in all of this, in front of this, it's still challenging to characterize the 2D material very massively. So the first challenging is to check the thickness. Using our naked eyes is very easy. So we use this contrast to distinguish the thickness of the 2D material. But for the machine, it's at the beginning very challenging because we need to combine the computer vision domain knowledge and the 2D material domain knowledge. But it's not challenging anymore at the moment because a lot of researchers from very beginning using the computer vision and then the deep learning and then the segmentation, we can recognize the image of the 2D material through contrast with different thickness of each pixel. So we call it segmentation. This is a typical classification task that we recognize thickness pixelly. But for the 2D material, we have a hot topic like twist angle. That means in each layer, we have different twist angle with respect to each other. Either bilayer or three layer, we have different kind of combinations of different layers. In our using our naked eyes, it's not a big challenge. We can recognize the edge, then we calculate the angle. Also, we have some other reference like a second harmonic generation that to recognize this angle more precisely. But this is very time consuming. Why not finish this twisted angle recognition autonomously? What's the difficult there? The difficult part is we need large amount of data set. This is very challenging. Even we use CVD, we can only see this thermodynamically stable at 0 degrees, 30 degrees, 60 degrees, but the twist angle in between is always missing. Therefore, we cannot reach a large amount of data sets. What we can do, we learn from like autonomous driving domain knowledge is we can use synthetic data set. What does that mean? We can use OpenCV to generate different patterns to have this synthetic looks like very much like the grown substrate. So we can use this to train our model. We can generate like 10,000 or even more different kind of pattern, different kind of images to fit through the ResNet model. Then we can recognize the twist angle. It's just a number. It's what we do is we input the image from the last stamp for the already recognized thickness. Then we put it into our ResNet model, and then this ResNet model is trained by all these synthetic data set. So in this case, we have output with just a single number. This single number is just your wanted twist angle number. So this is very efficient. It's already calibrated by the second harmonic generation that our model is very efficient. Also, we can use this thickness and twist angle recognition to feed back to our growth parameters to optimize our growth. So this is for the very simple and intuitive demonstrated that the deep learning can be very useful in this recognition of the device or the material. The second challenge is for the device verification. Normally for device, we have the traditional integrated circuit method that we have the material and then we do all this nanofab, we do this lithography, and we have a device. But for 2D material, we have the advantage that we can peel off the 2D material from other donor substrate. Therefore, we can make the electrode first using a very traditional method, and also then we transfer the 2D material on top. So we can do this at the very beginning use E-beam lithography, but recently we found out that this is it can be even simpler. We use this 3D printer used for print some plastic part. This is very cheap, just 200 euro. So we use this. This has a light source of 405 nanometer of light source, and then it has this LCD screen. This LCD screen can be programmed or can be designed with your with your own pattern very easily and in a very short time. So in this case, we can reach the 2-inch wafer electrodes with a sorption distance of 20 micrometers. So this is could be very useful for sensor people, and also it can be reached at 2-inch wafer scale in a very cheap way. Therefore, it not only for sensors but also probably for microfluidic people, you can use this technology for your research. I hope this can bring some interest to the industry of from the lab different level. The second challenging is for the lab instrumentation control. So as a electrical engineer or material science or chemist, you always familiar with Kisely. So probably it takes several days to be familiar with it. And then you get some script from the GitHub. But for some unconventional or even you design some different, you put different instruments together, like 10 different instruments together. And this synergy or orchestra different instrument is still very big challenging for the researchers or the engineers. So typically we need a software developer. This software developer is expertise on this coding, but now it's not necessary anymore. So we can use the rapidly developed large language model to help us design our script autonomously. What's the idea behind that? Is first we work on each individual instrument. Each individual instrument have two parts actually. It has an interface between the instrument and the computer, and then you have your own logic. You want to measure the voltage, you want to measure the current at another time, and then you want to have different voltage in the current level. All this logic can be designed easily if you have the interface guaranteed. Therefore, we make all these prompts without each coding line of Python or MATLAB. We only have this prompt with the instrument. Then we make each instrument work, and then we design our complex functionality through another different kind of prompt. So with this simple kind of open source methodology, we can have a single pixel camera or kind of photocurrent mapping. This is complex and tough. Also, now we are working on more combine like 4 or 5 or even 10 different instruments together. So this still works. So what's more, we can use AI agent. What AI agent means so you use this large language model, you use natural language to interact with API, with API like OpenAI, like Kimi, Moonshot, DeepSeek. Then this API with a proper prompt can design the Python code itself. And it has this Python code to interact with the instrument and collect the errors from the instrument. In this case, it's a closed loop kind of method. So we can have the IV sweep in 10 minutes without any interaction of the human. We only design the prompt and the Python code for the AI agent. So this could be a revolutionary methodology to for your lab. So if some industry people or some researchers is interested in this topic, I'm basically very much put my effort on this domain. So we can discuss more on this topic and push it to commercialize to do more work. So we can either further push this with the Internet of Things to show the education side of this method. So in the end, I also want to show so not only we can use the AI to help us, but also we can use AI like deep learning to increase the functionality and the accuracy of our device. Here, the example is we combine the commercial photodetector or the LED arrays with different temperature sweeping and also the deep learning, we can have reasonable low cost and high accuracy spectrometers. So this idea can be extended to different kind of domain like 2D material I will show later. So strain, why I like strain for the material? Because strain with this kind of magic force on the materials, especially the semiconductor material, this can increase the mobility of the materials dramatically. In 2D material, there's still a lot of open questions on this topic. So we have different kind of training methodology to apply to the materials. So there are these simple ones, you just simply bend the substrate, and there are some complex ones. You can use MEMS actuator to stretch your material. This is pure mechanical strain. So this is the most difficult one, but this is the most applicable one. But this is easy one, so we start with easy methodology. It's like work like a wind tunnel. So in the wind tunnel, you can use a low cost, very low cost, very simple methodology to test your ideas first. So we just use this strain setup with 3-point bending or 4-point bending with this rod. It's controlled by motorized stage. I will show later. You can calculate your strain level simply by this equation. So in this simple method with 3-point bending, we can do lots of tests already, like test the homogeneity, like test the strain transfer. But in order to check the properties of the band gap, we have simple method like a differential reflectance. What does that mean? With just two spectra, either on the substrate or on the materials, you can have the ratio between the absorption and self-absorption is the intrinsic property of your materials. Therefore, we can have A excitone and B excitone easily distinguished. With different layer thickness, for example, like MS2 have a dramatic change with the band gap from monolayer to bilayer, trilayers. So the peak of the differential reflectance is totally different for different layer thickness and also with different strain level. In this method, we use the motorized stage to gently strain or control the strain level very precisely, like 20 nanometer per step. So we can combine the high throughput calculation like differential reflectance, and also we can change the electrical property and also the optoelectronics property of the 2D device. So you can see here it's very interesting that with 1% of strain, the photo response increased 5 times. That's a huge amount of enhancement because of the increase of mobility of the device with tensile strain. Also, because of the Schottky barrier is lowered by the tensile strain. So we can not only working on isotropic material like MS2, also we work on ionotropic material like IES2. So then using this simple platform, we can have the photodetectors already, but if we using strain to tune the response curve of the photodetectors, plus the deep learning, we can have high accuracy and small sized reconstructive spectrometers. This is because my also have my own experience on MEMS technology, then why not we combine MEMS with 2D materials using the simple idea as before that we can use MEMS to stretch the material or compress 2D materials to change the properties of its electrical properties or optoelectronic properties. In this case, we can have high accuracy reconstructive spectrometers. We are working on that at the moment. So the take-home message is with AI, like deep learning, we can autonomously check the 2D materials. Also, with the large language model, we can lower dramatically the barrier of lab automation. So also with if we combine strain, the tuning log, and the 2D device, and also the deep learning, then we can have high accuracy and low cost and small size reconstructive spectrometers. So that's all my talk. So I would like to thank all my collaborators and from China, and also my students from China, and also my students in Europe. And thank you all. Without their help, I cannot achieve what I get now. So I hope you have some questions, you enjoy my talk, you learn something. And if you have more questions, you can either send me some email or you can add my WeChat. Please enjoy. Thank you.